Hi everyone, welcome back. Today we're going to be talking about standard P4, which is negative and rational exponents. Our objective today is that you will be able to write a function as a rational exponent to a radical and vice versa. And you will also be able to apply the properties of exponents to simplify each. Now we have one big idea that we need you to understand today. And that idea starts with the idea of fractional exponents, right? What happens when I have a value and I raise it to an exponent, but that exponent is really a fraction? And what it turns out is that there is a relationship between this, and another way you can think about it is if you were to take the nth root of something and raise that to the m power, that these two ideas would be equivalent to one another or equal to. Now, in fact, this is how we most commonly see it, but there is another way to think about this as well. Sometimes people think about it as the nth root of a raised to the m power on the inside. So sometimes it's that whole quantity that's being raised to the m power, as we see in this green one here that I'm highlighting. And sometimes, as in the one above it, we see it with that m inside. We can kind of switch between those two however we want. Now, it is kind of important to know here that whenever you see something with that fractional exponent, we think about the m as kind of the exponent, and we think about the n as the root. Okay? And the root being kind of the index number on your radical over there. We'll talk more about that. I think you'll be pretty refreshed on it because I believe you've seen this quite a bit in Algebra 2 already. Our first example here says to write as a rational exponent. What that means is rational just means fraction. Right? So we want to write this with a fractional exponent or an exponent that is a fraction. Now, looking at this, we can see that we have 2 being raised to the 4th, and then we're taking the 3rd root of that. Well, according to what we wrote down up top, right, this is really in that exact same format right there. So I would take whatever the index is, which in this case is 3. It's that outside root number. That's going to go on the bottom, right? So this is the same as saying to the 4/3 power, right? The 4 is our m value, so that's what goes up on top. And the 3 becomes our n value. That's what's going to go on the bottom, making this our answer. Right, so we're going to try to write all of these with a fractional exponent. So here's our next one right here. Now you might notice that this one does not have a power on that 4. So anytime something doesn't have a power, we can think about it as being raised to the 1st power. And when that happens, we could come over here and rewrite this. If this was what we had, then 1 would represent m, and 3 would represent n, so I could write this as 4 to the 1/3 power. Looking down at this next one, this one follows the first definition that we were given more. You can see that first definition right here, where we have parentheses around that whole quantity, and this can actually still be written the same way. This is still our big exponent here, so I'm still going to have -2 to the 3/5 power. The 5 still goes in the denominator there. Now, one thing we need to be careful of with these is when I have these quantities, right, it's this whole -2 that's being raised to that power. If I don't have parentheses around that, then what my calculator and what anybody looking at this would assume is that it's just 2 to the 3/5 power, and the negative is just going to slide in front. Right, so I want to always make sure that if it's dealing with that whole quantity that I put parentheses around the whole thing. I don't know where my 3 went. Here's another one for us. Now you'll notice that this one does not have a number in the index right here. And the reason for that is because this thing is really a square root in this situation. Now, as we've discussed previously, every radical really has a number sitting there whether we can see it or not. And when there is no number sitting there, that number is just assumed to be a 2. Right? That's what tells us that it's a square root, that it's something squared equals that. So when I get to this situation here, I would actually say that this is 3 to the 5/2 power. Right? So if we don't see a number up in that little index spot to indicate the root, we just assume that it is a 2. Looking at our next problem over here, we've got to be a little careful with this one now. Right now, I have x being raised to the fourth power. This is not 8x raised to the fourth power. And that's why we got to handle this one a little bit more carefully. Now, if we think about this, this whole thing is really being raised to the first power, right, since I don't see anything out there. So if we go back to our first definition of this, we could really rewrite this as 8x to the fourth. I'm going to put that in parentheses because all of that's there. And then we're taking the fifth root of that, so we know we're going to have a 5 in the bottom of that exponent. And then it's all being raised to the first above that. We got to handle this one a little bit more carefully because this 4 is not being attached to all of this. Now, I do want to look at this just one slightly different way. Had this been written like this, where we're looking at the fifth root of 8x all to the fourth power, then there would have been no need to put these parentheses around the outside because of the fact this 4 is already going to both of those. So using the other definition of those rational exponents, I could have written this as 8x to the 4/5 power in this situation. Right? So that's really the difference between having a set of parentheses here and not having a set of parentheses there. Two completely different answers, and that's really what we want to be careful of as we're working through these problems today, just that we're thinking about that intentionally. Here's the last one. Right now, since this 2 doesn't have an exponent, we could think about that as a 2 to the first. And since we don't see an index on this, we can put the 2 there. Remember, anytime there is no index, it's always assumed to be a 2. So I could write this as 2 to the 1/2 power. So think about what that's saying right now, is that if I took a number and I raised it to the 1/2 power, that is the exact same as if I look at the square root of that number. And we can even test that out if we wanted to. 9 is a perfect square, right? So if I took the square root of 9, I do know that I would get a 3. But according to what we're showing right here is that if you actually take 9 and you raise it to the 1/2 power, you also get a 3, right? Those two ideas are equivalent to one another. Moving along, down here it says to evaluate. Whenever we want to evaluate, we want to see what this is actually equal to. So with today's lesson, today's big lesson focuses on switching between either dealing with something with a fractional exponent or dealing with the root of a number raised to another power. So looking at this, we can just try to change this up if we're not sure how to go about it at first. But this is really saying we're equal to 4, or I'm sorry, the square root of 4, right? Because that was our 2 there. And all of this raised to the 5th power. So looking at that, if I just wanted to know what the square root of 4 is, we should all know the square root of 4 is just equal to 2. So now I really have 2 to the 5th power, and 2 to the 5th power is just 2 times 2 times 2 times 2 times 2, which would be 32. Now, technically our calculator should be able to compute this as well, but really to show you know what you're doing on these, you're going to want to be able to break stuff down how I just showed you to over here. If you just simply come over here and write equals 32, you would not be getting full credit on that. Now on our calculator, again, if I take 4 and I raise that to the 5/2 power, I can see that I get 32. So I have a nice way to check it on this particular problem. Here's another one. Now we're going to look at it on our calculator in a minute and make sure that we got the right answer. But before we do that, we're going to actually sit there and try to evaluate this by hand. Now, one thing you might notice right off the bat is this negative exponent. Remember, we've talked about this previously. Whenever we have a negative exponent, that's the same as basically saying take whatever's in the numerator with that negative exponent, move it to the denominator of a fraction, because this really is 9 to the negative 1/2 power over 1. And when you move that down there, the 9 to the 1/2 now becomes positive. That exponent flips when you move it from the numerator to the denominator or from the denominator to the numerator. The sign on it does. We still need to hold our fraction with a 1 though. Now, kind of as we saw earlier, when I have something to the 1/2 power, we can rewrite that as it's just the square root of 9 to the 1st 9 to the first is, of course, just equal to 9. So we're dealing with the square root of 9, which is obviously 3. So in the denominator of this fraction, I really just have a 3 that's sitting down there, and I have a 1 up top. 1/3 as a decimal is 0.3333. So we can check our work here by actually just typing in 9 to the negative 1/2. And you can see we also get that 0.3333, which is equivalent to the answer of 1/3 that we got. Now again, today's lesson, ladies and gentlemen, focuses on switching between there and knowing how to manipulate those. So just giving me an answer of the decimal approximation is not going to be good enough on your homework. You're going to get no credit for that. I want to see those in-between steps. Here's another one. Again, negative exponent. To fix a negative exponent, which is the first thing you always want to do, we're going to take whatever is being raised to that negative exponent and move it to the denominator of a fraction. So if I move that down to the bottom of this fraction, that exponent will now be positive. So on the bottom, I'm going to have a negative 81. Still going to keep that in parentheses, raised to the 3/4 power with a 1 on top. Right? The 1 is just holding that fraction since there was nothing else left up there. Now, looking at this, this is telling us to take the 4th root of a negative 81 and then raise that to the 3rd power and then take 1 divided by that. Now, on the paper, this looks fine, but mathematically this doesn't check out for us. And the reason for that is because of the fact inside here we have a negative. Now, one thing to note, I don't think I discussed it already, is this whole quantity right here is negative. When this moves to the bottom, it does not become positive. Only the exponent changes its sign when it moves from the top to the bottom. So we still have a negative down there inside. Now, thinking about this, right now, when I look at the 4th root of a number, right, I'm asking myself, well, if I had 81, 80 or negative 81 is equal to some number times some number times some number times some number. And each of those numbers have to be the same, right? If I raise something to the 4th power, it needs to be equal to a negative 81. Here's the problem with that. If I had 3 times 3 times 3 times 3, right? 3 to the 4th power. That would be equal to 81, but it's not equal to negative 81. If I had negative 3, right, so I'm going to use my parentheses, to the 4th power, that is also not equal to negative 81. And the reason for that is because every time I have 2 negatives, I get a positive. 2 negatives get a positive, and a positive times a positive is a positive, not a negative. Now, the way exponents work is you have to multiply the same thing by itself that number of times in order to get your answer. So looking at this, we see pretty quickly that there's no number I could multiply by itself 4 times where I would get a negative out of there. Which means we have no way to compute the 4th root of this because it's not going to give us a number. There is no number that makes that true, which means there's no number we could cube, which means there's no number that we can divide by. So in this situation, we would say no real answer. Sometimes we might even say that no solution. But there's no number that can be evaluated out to be. Now, looking at this, let's see what happens if we try to punch this in on our calculator. Negative 81 raised to the negative 3/4 power. Again, our calculator even knows that is not something it can evaluate. So there really is no answer to that. So let's keep going through these. Again, we have some properties of exponents here. You should be very familiar with these. If you are multiplying 2 things that have the same base, right, a and a, you are going to keep the same base and add the exponents. If you have something with a power and you raise it to another power, you multiply the powers together. If you have 2 quantities and they're both being raised to the power goes to both of them, right? So each of them are going to get an m. One way I like to think about this is if this was like a 1 and a 1, the m gets multiplied to both of them. Right? Parentheses mean multiply exponents. That's why these got multiplied as well. The negative exponent property we've discussed a little bit. When something has a negative exponent, if you put that over 1 and you move that piece to the bottom, that exponent is now going to become positive, and you can evaluate that. One thing to note is that only works if a is not equal to 0, because if it was equal to 0, we'd end up dividing by 0, and that, of course, is bad. We also have the quotient of powers. If I have something with the same base on top and bottom of a fraction, and they have different exponents, you can take the top exponent and subtract the bottom exponent to get your answer. Keep that same base. And last but not least, this kind of is the same as these two up here. If I have parentheses, I always tell my kids parentheses mean multiply exponents. 1 times m would be m, 1 times m would be m, so I'll get a to the m over b to the m. Let's look at these. Now we're going to try to practice with some of these rules. You've gotten really good at working with those rules when you're dealing with just whole numbers. Now we're going to kind of expand on that a little bit, where you're going to start to deal with those rational or fractional exponents. So looking at this, parentheses mean multiply exponents, right? We can see that this matches up with the product of a power rule up top, and we need to multiply exponents. So up here, if I had x, right, that was my base, that's still going to stay my base, and my exponent is just going to be whatever 3 times 1/6 is. Now this is a great time to review some of your fraction rules. If you were trying to multiply fractions, you just multiply the numerators and the denominators. So one way we could think about this is instead of thinking as just 3, let's rewrite it as 3 over 1. 3 over 1 times 1 over 6 would be 3 times 1 in your numerator, 1 times 6 in your denominator, and that, of course, reduces to be 1/2. So we could rewrite this as x to the 1/2 is what this simplifies to. Or we could also rewrite this as the square root of x to the first power, right? Because we should be good at switching between those. That is what today's lesson is all about, is that switch, right? So we always want to think about that. Remember, this is your root, that's your power. Let's do another one. We have x to the 1/4 times x to the 1/3. I'm going to do this one in orange so maybe you can see where these are color coding with the rules. That is just a horrible little star up there. The last one wasn't great either, but we'll take it. Whenever two things have the same base, which these do, they're both x, and different exponents, to combine them together, you keep the same base, but you do need to add the exponents together. So 1/4 plus 1/3. Now in order to add fractions together, you need to sit there and get a common denominator. Our common denominator will be 12, so I would need to multiply this by 3 and by 3, and this by 4 and by 4 to get that common denominator of 12. So multiplying across, I will have a 3 over 12 and a 4 over 12. And once I have a common denominator, I can add my numerators together to get a 7 over 12. So my final answer is x to the 7 over 12. And while we're here, let's just write that as a radical. So writing it as a radical, that would be the 12th root of x to the 7th power. Nice. Moving ahead to the next one. In the next problem that we have, we see that we have two things with the same base that are being divided. So according to our rule up top, maybe I should change my color again. This matches up with our quotient of powers rule. And what that says is you can take the top exponent and subtract the bottom exponent while keeping the same base. So my answer would be x. My top exponent was 2/7 minus, now notice this is already a -7, so I want to minus a -7 here. Now a couple things. Two negatives always make a positive, so this is the same thing as saying 2/7 plus 7. Since we're trying to add with a fraction, let's get a common denominator. So if I put 7 over 1, my common denominator would be 7. So I'll multiply by 7 and by 7. And this already has a common denominator, or already has our 7 as a common denominator, so that will be good. So we'll be left with 2 sevenths plus 49 sevenths, which is equal to 51 sevenths. So my final answer here would be x to the 51 sevenths. Now, writing that with in radical form, that would be looking at the 7th root of x to the 51. Last problem, here we go. This one is unique. And the reason for that is this one is actually starting in radical form for us. Now, best advice I have for you is if you're given something in radical form right here, what you probably should do is convert it to exponential form, or that form where you have that fractional exponent, because that's really the point we're trying to have you process, right? So think about it as all of this is being raised to the first power, which means I could rewrite this as x to the 15th over y to the 3rd raised to the 1/3 power. And if I raise something to the 1/3 power, then I would just multiply my exponents here, right? So this is matching up with our power of a quotient rule, meaning that exponent on the outside gets multiplied by the exponents on the inside. So I would get x to the 15 times 1/3 over y to the 3rd times 1/3. Of course, 15 over 1 and 3 over 1. Multiplying across the top, I will end up with x to the 15 over 3 and y to the 3 over 3, which lastly will equal x to the 5th over y to the 1st. And we're done. Really, the secret to this problem was just the fact that if you took this and you rewrote it right here, right away, everything seems to match up. If you don't do that, you look at it and the wheels start to spin, and it's hard to really get started. One last big idea we got to talk about are just some properties of radicals. Now, these properties of radicals say that if I look at the nth root of a times b, that's equal to the nth root of a times the nth root of b. You can kind of break this up into two separate radicals, right? Divided in half, this is now the nth root 2. And the same thing works for division, right? The nth root of a over b is the same as the nth root of a divided by the nth root of b. Now, in order for these two properties to work, the one caveat that we got to consider is the fact that the radical must be the same. Or I'm sorry, even the root on the radical must be the same. If we have different roots, we can't combine in this manner. Looking at this first one, we have two radicals that are the same being multiplied together. So that means I can rewrite this as the cubed root of 25 times 5. Now, if that 25 times 5 is inside, we certainly can evaluate that. 25 times 5 would be 125. And now we're just asking you, well, what is the cubed root of 125? That means what number times itself is equal to 125? And the answer is 5. And our calculator could have shown us that as well. Now, you should know how to look at the third root of a number on your calculator. Assuming you have a graphing calculator, if you hit math, and then for me, it's option number 4, which I'm seeing kind of right here, or just even with that. Option number 4 has a little cubed root here. And if I look at the cubed root of 125, I do see that that ends up being equal to 5, and we'll take that as an answer. Here's another one. Now, on the surface, you might think to yourself, well, oh, we can just combine these like we did on the last one, but in fact, we can't. And the reason for that is because these do not have the same root. This one is a third root, and this one is a fifth root. So, looking at this, really the only thing that we can do is let's just see if we can find a third root of 729. So, looking at our calculator, again, we'll go to math, third root, 729. Hey, that is equal to 9 over the fifth root of 3. I think that's where I'd leave it. You can't push those two things together because they are not the same radical, so this would be as far as we could go. Now, I'm starting to doubt myself a little bit because this is a weird problem to show you where you can't really do anything. So maybe I put a typo in there. So I'm just going to try to break this down and give you a different problem to consider for a second. If I had this as the third root of 729, and let's just pretend that that would have been the third root of 3, if those two are really the same, then this is really the same as the third root of 729 divided by 3. And if I can get that far, which I couldn't in the original problem, but in my changed one I could, then I could actually divide 729 by 3, which is 243. And we're still looking at the third root of that. So looking at the third root of 243, we don't get a nice number, but this seems like we're okay. Really what I want you guys to know is just, I want you to understand that rule. How if those are the same, they could be put together in that way, and if they're different, they can't. All right, so looking at this problem, the way I think I would start this problem is maybe let's look at this with a radical in mind. So since all of that's being raised to the 2/3 power, we could look at that as the third root of 8, a to the second, b to the third, with all of that being squared. Right? That's how these two ideas would relate to one another if we flip that idea or that thought around. Now, looking at this, inside, I do notice right away that I could distribute this 2 into the inside here. So I would end up with 8 to the second power, a to the fourth power, and b to the sixth power. And all of this is just the third root. Now, in order to simplify this radical, we could actually go a little bit further with this. 8 to the second is, of course, going to become 64. Now, to simplify this, we are looking at a cubed root right now. And while we haven't done a lot of simplifying with these, this is still something that should be coming back from Algebra 2. So breaking down 64, I could break it into 2 and 32, which I could break into 2 and 16, which I could break into 2 and 8, which I could break into 2 and 4, which I could break into 2 and 2. So I can really rewrite 64 as 2 times 2 times 2 times 2 times 2 times 2. So right now I'm looking at the cubed root of 2 times 2 times 2 times 2 times 2 times 2. I'm also going to be having 4 a's inside, and I will have 6 b's. Now, as we talked about earlier last week, whenever I'm trying to evaluate these, the way I like to think about it is like a 2-for-1 special if we're doing square roots. But whenever this number is a 3 on the outside, I need 3 of the same thing in order to pull 1 to the outside. So I'm going to be able to pull out a 2. I'm going to be able to pull out another 2. I'm going to be able to pull out an A. And I'll be able to pull out a B and a B. So looking at this is all going to look much simpler now. I'm going to have a 2 times a 2 times an A times a B times a B on the outside. And then I'm going to have the cubed root of A left on the inside. So simplifying this, I could have 4AB cubed roots of A. Right, so definitely was able to make this a little bit simpler and nice to think about here. And more simplified, right? Here's another problem for us to consider. So if I have a to the 5/7 times b to the 2/3 all over c to the second. What we can do to start here is let's first start by multiplying the 7 by each of those inside exponents. Doing that, I will have a to the 5/7 times 7 times b to the 2/3 times 7 all over c to the 2 times 7. Simplifying that, I know my two 7s are going to kind of cross cancel there, so this would end up just being a to the 5th. For my b term, I would have b to the 14 over 3. And finally, I would end up with c to the 14th. And we're done, right? Because none of those have the same powers. Let's leave it right there. Another problem for us to consider. You could tackle this a couple different ways. The idea that's coming to me is let's multiply this by each of the powers that we have on the inside. So this would be the same as saying x to the 4th times a negative 1/2 over 64 to the 1st times a negative 1/2. From there, 4 times a negative 1/2 would leave me with a negative 2. And on the bottom, I would have 64 to the negative 1/2 power. Now, since these both have negative exponents, we should never leave an answer with a negative exponent. We're going to move this guy to the bottom to make that exponent positive. And since this is negative, we're going to move this guy to the top. So I will get 64 to the 1/2 over x to the 2nd. One last piece we can consider on here. We know that anything raised to the 1/2 power is just the same as saying let's take the square root of it. And of course, the square root of 64 ends up being equal to 8. If you're confused on how we got there, if I had 1/2, remember this would be the same as the square root of 64 to the 1st, which then simplifies to this guy. So my final answer would be 8 over x to the 2nd. One other way I could consider that is if I wanted to look at this through a slightly different lens, I could have moved all of this to the bottom of a fraction to start, right, since that has a negative exponent, and work through from there. Last problem we're going to be tackling today. We have the third root of 40x to the 4th times the third root of 3x to the 6th. If you notice that these two things have the same root, great job. Since they have the same root, we can put them together under one square root. So 40 times 3 is 120. X to the 4th and x to the 6th will give us x to the 10th. Now we should go through and simplify this if at all possible. So looking at this, 120 would break into 2 and 60, and 2 and 30, and 2 and 15, and 15 is 3 and 5. So again, since we have a root of 3, we need to do a 3 for 1 special. We got to pull out 3 of the same thing in order to pull 1 to the outside. So this is the same as 2. Right, so we'll have a 2 on the outside. We'll still be dealing with the cubed root. Inside, 3 times 5 is still going to be 15. That was all that was left over of that number, that 120. And if I have 10 x's, that would be three groups of x's that could be pulled out. Right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 3 x's for 1. So we have 3 groups of 3 x's that'd be able to be pulled out with 1 x left over. So I'll get x to the 3rd on the outside, x. making this our final answer. Definitely lots going on today, guys, with those rules and knowing where to stop and where to finish. Make sure you're referring to the answer key that is posted with these as well. And if you have any questions getting there, please don't hesitate to reach out and we can chat about this in person as well. Your homework for today is worksheet P4. You are going to be tackling the evens and problem number 5. Thanks for watching. Have a good day. Again, let me know if you need anything.